Welcome back to AI Foundation Learning. Today we're tackling one of the most critical aspects of autonomous AI, decision-making. From self-driving cars to virtual assistants, decision-making is at the heart of any agentic AI system. But how exactly do these systems decide what actions to take? Whether you're new to AI, an enthusiast, or a seasoned professional, this video will give you a clear understanding of how decision-making works in agentic AI. We'll explore the algorithms that power these decisions, including some of the latest techniques used in the industry today. Let's dive in. At its core, decision-making in agentic AI involves choosing the best possible action based on the information available. Autonomous agents operate in dynamic environments, meaning they must continuously make decisions in real time to achieve their goals. Consider a self-driving car navigating through city traffic. Every second, it has to decide whether to accelerate, brake, or turn. These decisions are made based on the car's immediate environment and its ultimate goal of reaching a destination safely and efficiently. The decision-making process involves several steps: perceiving the environment, predicting possible outcomes, evaluating those outcomes based on a set of criteria, and then selecting the best action. To implement these steps, various algorithms and models are used. Now let's explore some of the most common algorithms used in agentic AI for decision-making. These include reinforcement learning, planning algorithms, and heuristic-based approaches. Reinforcement learning is a type of machine learning where an agent learns to make decisions by interacting with its environment. The agent receives rewards or penalties based on the actions it takes, and over time, it learns to choose actions that maximize cumulative rewards. RL is particularly useful in environments where the agent must learn optimal strategies through trial and error. Imagine training a robot to navigate a maze. The robot starts with no knowledge of the maze's layout. Using reinforcement learning, it explores the maze, receiving rewards for reaching the exit and penalties for hitting walls. Over time, the robot learns the optimal path to take. Popular tools for implementing RL include OpenAI Gym for creating simulation environments, TensorFlow and PyTorch for building RL models, and Google's DeepMind for advanced research in reinforcement learning. Planning algorithms are used to identify a sequence of actions that will achieve a specific goal. These algorithms are often employed in environments where the agent has a clear objective, but must consider various constraints and possible future states to reach that goal. Think of a delivery drone that needs to drop off a package. The drone uses a planning algorithm to calculate the most efficient route, taking into account obstacles, weather conditions, and battery life. The algorithm generates a plan that allows the drone to reach its destination while minimizing energy consumption. Tools like Google or Tools, *search, and Dijkstra's algorithm are commonly used for planning in AI systems. ROS, Robot Operating System, is also a popular framework in robotics for implementing planning algorithms. Heuristics are rules of thumb that help an agent make decisions quickly without having to evaluate every possible option. These approaches are particularly useful in environments where computational resources are limited or where decisions need to be made rapidly. In a game of chess, an AI might use heuristics to prioritize certain moves over others based on patterns learned from previous games. While not guaranteed to be optimal, heuristics allow the AI to make good decisions within a reasonable time frame. Heuristic search algorithms like alpha-beta pruning in game theory or greedy best first search are commonly used to implement these approaches. Implementing decision-making algorithms in agentic AI requires careful architectural design. Here are some key considerations. Modularity. A modular architecture allows you to separate decision-making components from other parts of the system, such as perception or action modules. This makes it easier to update or replace the decision-making algorithms without affecting the entire system. Interoperability. Your decision-making module should be able to communicate efficiently with other components of the AI system. This requires choosing the right communication protocols and data formats. Middleware solutions like ROS in robotics can help ensure smooth interoperability. Real-time processing. In dynamic environments, agents need to make decisions quickly. This requires optimizing your decision-making algorithms and choosing appropriate hardware, such as TPUs or GPUs, to ensure real-time performance, learning, and adaptation. An effective decision-making system should continuously learn and adapt to new information. This might involve implementing online learning techniques or integrating reinforcement learning models that can update in real time based on new experiences. Let's put these concepts into context with a practical example. Decision-making in autonomous vehicles. An autonomous vehicle needs to make a series of rapid decisions as it drives. Should it accelerate, brake, or change lanes? To do this, the vehicle uses a combination of algorithms. Perception sensors like cameras and LiDAR gather data about the environment. Prediction. The vehicle predicts the behavior of other road users, such as whether a pedestrian will cross the street. Planning. A planning algorithm determines the best route to the destination while avoiding obstacles. Decision-making. Finally, the vehicle uses reinforcement learning models to decide on the best immediate action, such as adjusting speed or changing lanes. By integrating these components into a cohesive system, the autonomous vehicle can make safe and efficient decisions in real time. As we've seen today, decision-making is a complex but essential part of any agentic AI system. From reinforcement learning to planning algorithms, the tools and techniques available today make it possible to create intelligent agents that can navigate even the most challenging environments. If you found this video insightful, be sure to give it a thumbs up and subscribe to AI Foundation Learning for more deep dives into the world of AI. And don't forget to hit the bell icon so you never miss an update. Thanks for watching and see you in the next video.